So here we have our last two tests for convergence, ratio and root tests. Before we start on that, let's review the other tests that we've learned. So we have these 6 tests. Pause the video and decide which test you should use for each of these series. So when you look at this one, other than memorizing that it's this harmonic series, it diverges. We could also use the integral test for this. We could use the P-series test also. So looking at this one, it is in the right form for a P-series test, and it'll converge because 2 is greater than 1. And here, when you see an exponential with a variable exponent, consider the geometric series. This is geometric, and the common ratio is between 1 and 0, or between 1 and negative 1, so that will converge. Here, the overall degree is 1 over n to the 1/2, because this n will cancel one of these, and we'll end up with a 1/2. So we think it diverges, and we could use the, looks like we can use the comparison test there. Here you can use the nth term test, because the limit of this is 1. And on this one we have overall the degree is 1 over n, so we think it diverges. So we're either going to use the comparison or limit comparison. It diverges, and we have the denominator smaller, so it looks like we can just do direct comparison on that. Alternating series, so then we're going to use the alternating series test. I didn't write that up there. But this will converge because it satisfies the 3 conditions for alternating series. The sequence is positive, decreasing, and the limit is 0. And then once it's alternating, that will converge. Here we have overall the degree is 1 over n, so we think it diverges. And we will either do the comparison or limit comparison. We can also do the integral test because of that relationship there. We could do substitution. All right. So for the ratio test, we're going to look at a ratio of the next term over the current term. So let's compare the ratios for all of these series, and let's look at the sequence. So when n is 0, we get a 1. When n is 1, we get a 1/2. When n is 2, we get a 1/4, and 1/8, and 1/16, 1/32. Let's then look at this ratio. In a geometric sequence, we've always been looking at this ratio where we have 1/2 divided by 1. Then we have 1/4 divided by 1/2. 1/8 divided by 1/4. And we have a common ratio. So that's what we've been doing ever since Algebra 2. We have a common ratio. And we know that that means that the series converges. And then we look over here, we'll have 1, 3, 9, 27. If we look at this ratio, 3 divided by 1, 9 divided by 3, 27 divided by 9, and here we have a common ratio, but it's greater than 1, so we know the series diverges. And now let's look at this. When we put a 0 here, 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, and 3 factorial is 6, 4 factorial is 24, and in case You're missing that. Remember that 4 factorial equals 4 times 3 times 2 times 1. So we get 24. And here we had a 1 over 120. Now let's see what's happening to the ratios. Here we'll have 1 over 1, 1 half over 1, 1/6 over 1 half. 1/6 divided by 1 half is 1/3. Here we'll have 1 over 24 divided by 1 over 6, and that's 1/4. This is 1/5. So we see the ratios are decreasing, with the exception of this one. If we had a 1 half and these all stayed 1 half, then it would be like having these ratios of a geometric series, a convergent geometric series. But not only do we have a 1 half, but the ratios get even smaller, which we want small ratios for it to converge. A large ratio diverges. So we can see that if we just look at the limit of the ratio, and that limit is less than 1, then we could say that the series will converge. So that leads us to the ratio test. So, like we saw here, the limit of the ratio is 0. Well, the limit of the ratio is less than 1. So that means this series will converge. This series converges because its ratio, the limit of the ratio, is less than 1. If we have the limit equaling 1, then it doesn't work. We have to do something else. And if it's greater than 1, that means that the series diverges. And the ratio test is good for exponentials and factorials. So if you see either of those, consider using the ratio test. And we're going to have the limit as n goes to infinity of the next term divided by a current term. So we have a ratio, and the next term is written as replacing the n with an n plus 1. The current term, 2 to the n over n factorial. And we're going to look at the absolute value of that. Let's multiply by the reciprocal of that. And we don't have to write absolute value anymore just because n is positive. So then we're going to break this up, 2 to the n times 2 to the 1, and we'll start canceling. So 2 to the n times 2 to the 1, because n plus 1 would be the n plus 1 exponent. And then let's write n factorial, which is n times the number below it, times the number below that, etc., 2, 1. Here we have n plus 1 factorial, n plus 1 times the number below that, times the number below that, and times 2 times 1 all the way down, and a 2 to the n. We have 2 to the n divided by 2 to the n is 1. We have n factorial, n factorial. So all of this cancels all of this. And that's going to leave us with a 2 over n plus 1. And if we look at the limit at infinity, we'll have 2 over infinity, which equals 0. So that tells us, because the limit is less than 1, we can say that the series converges pause the video and try the ratio test on this one. Instead of writing the fraction, I'm just going to write this and then multiply by the reciprocal. I'll write this with an n plus 1, 3 to the n plus 1, n plus 1 plus 1. So I replace the n with an n plus 1, replace that n with an n plus 1, multiply by the reciprocal. And it's absolute value, but we have all positive numbers, so we don't need to write the absolute value. And let's break up that exponential, 3 to the n times 3. And we'll write out that factorial n plus 1 times the next number down, times the next number down, all the way down to 2 and 1. Here we have n plus 2, n plus 2 factorial, no, n plus 2 times n plus 1 times n minus 1, all the way down, and then a 3 to the n. So we have 3 to the n, canceling 3 to the n. N plus 1 factorial, n plus 1 factorial, and we're left with 3 over n plus 2. As n goes to infinity, this goes to 0, so we can say that the series converges, because the limit of the ratio is 0. Pause the video and try that one. So we'll copy this, negative 1 to the n plus 1, n plus 1 over n plus 1 plus 1. Do the reciprocal. I'll write this in the denominator, but it doesn't matter where the negative 1 goes. And it really doesn't matter because we have an absolute value. So we're just going to rewrite it without that negative. We have radical n plus 1 and why don't we put these radicals together? It would be n plus 1 over n, and we could write that as n over n plus 1 over n in the numerator. We could have n plus 1 over n plus 2. And if we just look at let's look at this one, we have limit as n goes to infinity of 1 plus 1 over n times the limit as n goes to infinity as n goes to infinity, that'll be a 0. We have square root of 1. And then here we have infinity over infinity, so we'll do L'Hopital's rule, which will give us a 1 over 1. The limit of the ratio is 1. That means the test is inconclusive. Instead of the ratio test, when you have especially when you have a radical or a polynomial, you should do some other test. And here we'd use the alternating series test. So looking at this, we have a positive sequence. It is decreasing, and the limit is 0. So then this will converge by the alternating series test. And this is like the other one. It's a polynomial with a radical, so we wouldn't use the ratio test is going to give us a limit of the ratio being 1, so that would be inconclusive. Here it looks like it's going to converge because we have a 1/2 and a 2, so the overall degree, we would be comparing it to that. And so that's going to converge, and we'll just have to use a comparison or a limit comparison test. So let's go on to the root test. And here we do the nth root. So we take the limit of the nth root, and if the limit of the nth root of the sequence is less than 1, then the series converges. Greater than 1, the series diverges, and the test is inconclusive if the limit of the nth root is equal to 1. So we will use the nth root test when we have something to the nth power, and let's make the connection to a geometric series. Here, this looks like it's geometric, but we don't have a constant ratio. But this is the ratio, and so this is just the ratio test. We're looking at the ratio. Does the ratio go to a number less than 1? Does it go to 1 or greater than 1? So when we look at the limit as n goes to infinity of the nth root So when we use this on something to the nth power, it's just going to cancel the nth power. And we have all positive numbers here, so we don't have to worry about the absolute value. And we end up with a problem similar to what we were just doing with the ratio test, where here is the ratio, and the limit in this one is going to be 3, because it's going to be infinity over infinity. We use L'Hopital's rule to get 3 over 1. So we know that the ratio is going to 3. That means that the series diverges. Pause the video and try that one. So again, we have something to the nth power, so that looks like a geometric series with a variable ratio. We want to know what's happening to this ratio as n goes to infinity. Limit as n goes to infinity, the nth root. We have all positive numbers, so we don't need to worry about the absolute value. We get n squared over 3n squared plus n, which is infinity over infinity, so we do L'Hopital's rule, and we'll have 2n over 6n. We can evaluate that. Canceling the n, we get 1/3. So the limit of the ratio is 1/3, and that means that the series converges. And that's the end of that lesson.